to begin chapter 18 by talking about electric potential energy. Our symbol for potential energy is still a capital U, and we can put a little E to indicate that we're talking about electric. You'll remember we're going to do a lot of comparing this in a way to gravitational potential and kinetic energy. Electrical forces are conservative forces. That's an important idea. Electric forces are conservative forces. Conservative forces, you'll remember, don't cause any loss of mechanical energy when they act on something. So conservative forces are either converting potential energy into kinetic energy or kinetic energy into potential energy, but conservative forces don't lose energy like friction. They don't convert it to non-mechanical means. We know that when an electric force, well, let's go back. When a gravitational force does positive work, it increases the object's kinetic energy. Think of a rock falling. When a rock falls, gravity's doing positive work, kinetic energy increases. The same is true for electrical forces. When an electric force does positive work, now what does it mean? Well, when the force and the displacement are in the same direction. And what happens when forces do positive work? Kinetic energy increases. When electrical forces do negative work, what's that mean? That means the force and the displacement are in opposite directions. Potential energy increases. All right, let's go back and think about our definition. And now really kind of a little bit simple when we say that the force and displacement are going to be in the same direction or they're going to be in opposite directions, because we know that they can actually be in any number of directions. Our formula for work is that work is equal to force times displacement. Whoops, not sure what happened there. Now, if they were in the same direction, we could actually stop there, but they're usually not. So we put cosine phi. Phi is the angle between the force, which is a vector, and the displacement, also a vector. They both have direction. Remember, work is actually scalar. So I didn't put the vector notation over here. Even though we're multiplying two vectors together, our result is a scalar quantity. And this, of course, is the formula for work, and this is really important. with a constant force. We're not considering the fact that the magnitude or direction of the force might be changing in this case. We just say work is force times displacement. We're assuming this value for this force is not changing. Okay, how can we get a constant force if we're talking about electrical forces? Well, one way is to have a uniform electric field. Force is constant in a uniform. Uniform means that the electric field is the same everywhere. Electric field. Well, how do we create a uniform electric field? The easiest is to take two parallel plates. We'll let this one be positive. It doesn't matter which one's positive or negative. And I'm going to let this one be negative. And we know that the electric field, I'll draw it in a slightly different color, points from positive to negative. So our electric field in between our two plates is fairly uniform, and it points from positive to negative. Now we know if we get over to the edges, it's not so uniform, but as long as we're close to the middle, it's going to be nice and uniform. Our definition of the electric field is that it is equal to the force divided by the charge. Remember, we get it in units of newtons per coulomb. So our force is equal to QE. That's the magnitude of the force that's going to be felt by a positively charged particle. Now, the direction of the force will depend on the sign. If I put a little positive charge right here, it feels a force this way. The electric field points in the direction of force on a positive charge. And of course, if you want to get away from the positive plate towards a negative. If I put a little negative charge in here, it will, of course, feel a force opposite the electric field. All right, so let's use this in our formula. Instead of F, we can put in QE, that's our force, delta X, cosine phi. All right, let's do an example and put in some numbers. Suppose that we have a uniform electric field, and they tell us the magnitude of the electric field is 4.50 times 10 to the third newtons per coulomb, and it points to the right, just exactly the way I've drawn it up above. First question, how much work is done by the electric field if a 3.50 nanocoulomb, I don't know if you remember nano, that means times 10 to the negative 9 coulombs. If a 3.50 nanocoulomb charge moves straight up 0.250 meters, so quarter of a meter. I'm going to draw that. I'm going to draw it in a different color. So they're saying, what if I take this positive charge right there and it moves straight up? Well, if you'll remember, our formula, in this case, the displacement and the force are perpendicular. If the force is perpendicular, that means we're going to be at a 90-degree angle. That means the electric field is not doing any work on it. Well, that makes sense. If the particle is moving straight up and the electric field points directly to the right, obviously it's not the electric field that's doing work on the charge. But if we put it in our formula, we can. QE delta X cosine phi, our charge, 3.50 times 10 to the negative 9 coulombs. There's our electric field, 4.50 times 10 to the third newtons per coulomb, so that's our force. Displacement, 0.250 meters. Cosine, and here we get it, our angle is 90 degrees. Cosine 90 is 0. This whole thing is 0. If the displacement is perpendicular to a force, that force is not doing any work. It's just like when you slide a box across the floor, the normal force, which is perpendicular, is not the force that's doing any work. Okay, so let's change it. How much work is done if we take the same charge but this time it moves 0.250 meters to the right. So we'll take that charge, or a charge. I've got a lot going on here. Maybe I better erase a little bit of it. Let's erase some of this. All right. There's our electric field. It points to the right. And they're saying, okay, so now let's just take a charge, to positive charge, and let it move to the right. Well, now the displacement's in the same direction, so we should get a lot of work. Same formula, QE delta X cosine phi, 3.50 times 10 to the negative 9 coulombs. There's our charge. 4.50 times 10 to the third newtons per coulomb. There's our electric field. Remember, QE actually is what's giving us our force. The displacement, 0.250 meters. And this time it's cosine 0. Well, cosine 0, you recall, equals 1. I didn't mean to shrink it. Okay. Put all of this in my calculator very carefully, and that came out to be 3.94 times 10 to the negative 6 joules. Finally, let's consider a case where we have a charged particle, but it's not moving perpendicular, but it's also not moving in the same direction as the field. So let's consider how much work is done by the electric field if the charge moves. We'll let it go farther this time. It's going to move 0.650 meters at an angle of 40 degrees above the horizontal. Now, if we want to, we can kind of draw another picture of all of this. I'm going to draw the uniform electric field. I'm not going to draw the parallel plates, but our uniform electric field is points to the right, like this. Our charged particle is moving at an angle, so here's our charged particle, positive, of 40 degrees. So this would be 40 degrees above horizontal. So now we do work equals Q E delta X cosine phi. We have the same charge, 3.50 nanocoulombs. With the same electric field, it was 4.5 times 10 to the third newtons per coulomb. We did change the displacement. We'll let it go a little farther. 0.650 meters cosine 40 degrees. So the work done in this case was 7.84 times 10 to the negative 6 joules. Just remember that when you are talking about a conservative force, when it does positive work, the object is gaining kinetic energy. So in this case, this was positive work. The particle would be accelerating and moving faster, just like if you drop a rock. When the electric field does negative work, in other words, some outside force is moving it, say moving a positive charge towards the positive plate, it's gaining potential energy, electric potential energy. Okay, let's continue now that we've kind of reviewed work. And let's think about potential energy of point charges. All right. Just like every mass has gravitational potential energy, due to another mass. Now, most of the time, we think of things having gravitational potential energy due to the mass of the Earth. But basically, every mass has gravitational potential energy due to every other mass. Okay? In a very similar manner, a charge Q I'm going to call it Q prime because there's going to be more than one charge. Just like when we do gravity, we have more than one mass. A charge Q prime will have electric potential energy. Due to another charge, Q. Now, we are not in a calculus-based course, so we do not have the integral calculus skills that we would need to develop this formula. So some of the formulas in this course we just kind of get as gifts. The electric potential energy U between two charges is K, Q, Q prime over R. That's electric potential energy due to point charges. What's the unit? Well, it's joules, just like any other form of energy. This is a scalar quantity, which means, of course, that it can be positive or negative. Now, you may think it's odd to think in terms of negative potential energy, but remember, really it's only changes in potential energy that are important. If this is the ground, we often this would be a height of 0. We often decide, oh, well, we're going to let gravitational potential energy be 0 at the ground. So if I have an object up here, its gravitational energy is mgh. It's potential energy. When it falls to the ground, its potential energy will be 0. But what if I dig a hole? There's a hole. Notice if I let it fall past 0, its gravitational potential energy at this point is actually going to be negative because I already decided that 0 potential energy was going to be right here. This one has gravitational potential energy of 0. This one's going to have positive gravitational potential energy, and this is actually going to have negative. So potential energy is a quantity that can be both positive and negative. That's different than kinetic energy, which has to be a positive quantity. All right. So just like gravity, we have to kind of arbitrarily decide where do we want electric potential energy to be 0. Well, look at our formula. U will equal 0 when the distance between the points, that's what R is. R is the distance between Q1 and Q and Q prime. K is still Coulomb's constant. We didn't develop the formula, but it was developed using Coulomb's law. So when R is equal to infinity, we are going to define gravitational potential energy to be 0 when the particles are infinitely far apart. All right, let's think about what that means in terms of signs, because we do have two types of charges. You know, there's only one type of mass. There's no such thing as positive and negative mass. So gravitational forces are always attractive. It's different with electrical charges. Electrical forces are attractive when you have two different types of charge, and they're repulsive when you have the same type of charge. So let's start with looking at what this means for like charges. So let's have our positive charge here. And we know that it has an electric field. And let's consider the potential energy of some charge Q prime due to Q. What's Q prime's potential energy because of Q? Well, I know if I get farther away, which is what's going to happen naturally, they're going to repulse each other. It's going to increase its kinetic energy as it moves away, and it's going to decrease its potential energy. If I keep going far enough, I'll finally get to 0 when R is equal to infinity. Notice, however, if I try to move the particle towards it, as I get closer and closer, as this distance between the two of them becomes smaller and smaller, my gravitational potential energy increases. To get closer and closer. That's a little different than the two masses. With masses, if we think about gravity, we have the most potential energy when we get higher and higher above the Earth, where that distance is bigger. But for like charges, which is, remember, this is not an attractive force, it's a repulsive force, the potential energy increases as I bring this charge closer and closer and closer. Bringing this charge closer and closer and closer is rather like compressing a spring. Okay. Now, I want you to realize that this sign will come out for potential energy when you use the formula. You do not have the absolute values. You have to include whether the charges are positive, or negative. In this case, if they're both positive, potential energy is always going to be positive. Unless, of course, they're infinitely far apart, in which case it's going to be 0. Same formula. Can't quite see it. Maybe I can. There we go. For unlike charges, opposite charges, the potential energy is always a negative quantity. So think about the same situation. We start here. Here's Q. I'm going to put some other charge over here that's negative this time. I want them to be oppositely charged. So here's a little negative charge I'm going to call Q prime. Notice the rule says, and our formula says, if they become infinitely far apart, if we go all the way out here, the potential energy is going to be 0 at infinity. But let's think about what happens. Which way does a negative charge naturally fall? It doesn't want to be pushed away. It's pulled towards this. Its potential energy is actually decreasing as it moves towards this. Okay? That makes sense because it's going to be negative. If you have an increase in magnitude of a negative quantity, you're actually decreasing. It's like 0, -1, -2, -3, all the way to negative whatever. It's decreasing. If you move it away from, which is what's going to happen this way, the potential energy increases, right? The natural motion of the particle is towards the positive. Well, as it moves closer, it's going to gain kinetic energy. Remember, the force is this direction. So it will gain kinetic energy, and it will lose potential energy. So we'll get a larger and larger negative quantity. Okay. Unlike charges, the potential energy will always be negative. Okay, I'm going to stop right here and do another video over the next section. I feel like just thinking about work and electric potential energy is probably enough.